طيب بسم الله الرحمن الرحيم. Today inshallah we're going to cover the last part in this chapter and then we'll go back to the textbook of the course and we'll continue the second part of the course. We'll cover basically wireless standards from the perspective of, again, providing quality of service. So what are the changes that we need to pay attention to as part of the wireless standards when it comes to quality of service? And the standards that we're going to cover are local area networks, the 802.11 and 802.11e. And then we'll cover the wireless personal area networks and wireless metropolitan area network. These are the three chapters in the textbook that we will cover in the next part of the course. So today the last part that we're going to talk about is related to recovery from packet loss. As we said before, some protocols like TCP, they provide 100% reliability. And as we said, that this is not something that we like for multimedia streaming, right? Because TCP provides reliability through retransmission, okay? And reliability through retransmission transforms any packet loss into delay. And delay, for us, is transformed into a play-out loss. And we define the play-out loss that the play-out loss happens when a packet arrives too late after its estimated play-out time. So even though the packet arrives, but this packet becomes useless, right? So in other words, we don't need to have retransmission, or we don't need to provide reliability through retransmission. However, although we have some multimedia streams like video, which is highly tolerable to packet loss, some other types of multimedia contents like audio is still sensitive to packet loss. Okay, so if we lose some packets as part of an audio file or an audio content, or particularly when we have interactive live chat, this actually affects the quality overall. Okay, so if we have one packet lost or two packets lost, this actually affects the quality. So in other words, we still need some kind of reliability, but not through retransmission, because retransmission introduces an extra delay which leads to play-out loss, and play-out loss still affects the quality. So here comes the forward error correction. So forward error correction talks about the fact that in order to become more reliable, we need to be proactive. We will not be reactive in the sense that we will wait until the error happens and then we retransmit. In the beginning, instead, we will be proactive in the sense that we will send the multimedia content with some level of redundancy. Okay? We will send the multimedia content with some level of redundancy. Based on that, we will be proactive and not reactive, and we'll see how we can do that. So today, inshallah, we're going to cover three major techniques for providing redundancy as part of the multimedia content. And particularly here, most of the examples here talk about audio as a type of multimedia streams that are both sensitive in terms of delay and packet loss, and particularly packet loss is what we care about today. So one forward error correction technique talks about the fact that for each n chunks, and chunks here are audio, small audio clips, or one packet, or maybe a group of packets, or one, if we're talking about video, assuming that we use the same technique for video, a chunk might be like a part of a scene or an entire frame or whatever, a piece of multimedia content that can be sent independently. So this technique talks about the fact that for each n chunks, okay, we need to introduce another extra n plus 1 chunk, which is the XORing of these n chunks. Okay? So that's the redundancy. That's the lowest level of redundancy. So the overhead that we have is that we have one for each n chunks. We have one extra chunk for each n chunks, which means that simply the overhead is 1 over n. Okay? So the overhead here is 1 over n. Type. So what is this technique going to give us? What happens is that if one packet, if one only chunk is lost, in that case, I can extract this chunk by having all the other n packets or n chunks and XOR them together. So if one of these n plus 1, if one of these n plus 1 chunks is lost, only one, okay? All you need to do is just to get all the other n chunks and XOR them together. You will get the extra one. Okay? So that's very simple. That's very simple. But the condition here is that we can have only one packet loss. If we have two packets, okay, whether they are consecutive or not consecutive. If we have two packets, we cannot extract them. We cannot extract anything. Alas, tough luck. So this gives us the indication that if the probability of losing one packet is a little bit high, we need to have n low or high. So we need to have low value of n or high value of n. Low, bravo. So we need to reduce the value of n here. We need to reduce it as much as possible. Okay? If we have n equal 1, this means that for each chunk we have another extra chunk, which means that we are doubling the stream. So if one packet is lost, we get the one next to it. That's it. If we have one packet or one chunk for each two chunks, this means that the overhead is 50%, right? And in that case, if we lose one of these two, we can get the other one, XOR it with the extra chunk, and we get the one in the middle. واضحة كده? So if, in other words, the stream is like we have. So the stream is as follows: we have 1, 2, n chunks, and then we have to get 1. So these are n chunks, and this is a n plus 1 chunk, and this one is actually the XOR of all these packets together. We align them on top of each other, and we get the XOR of all the bits. That's it. Okay? So that's this. If you remember, we have actually used the same concept more or less for error detection in 455 when you talked about data link layer. We used the same concept.
Dr. how XORing two packets will generate the bits of the lost one? Because it's the content of each packet is
it's different, but yeah, it's different. But as long as this one is XORed between all these, if you try to XOR it, so try it on two packets and get a third packet. Remove any one of them. You can get the other one by XORing the other two. That's a feature in XOR. Okay, it's very, very, very simple. You can try it using binary bits. You can try it. You will find it that it works. Okay, so so if there is any one of this, if any one is lost, I can get all the other n chunks, XOR them together, I get the extra. Okay? So, as we said, overhead is a 1 over n. That's the overhead. So, another thing that we need in order to measure the performance of this is what we call playout delay. That playout delay in case of one packet loss. Okay? So in case of one chunk is lost, what is the playout delay? The playout delay is, okay, so these n chunks, when can I recover all of them? Which means I can recover the lost packet or the lost chunk. When? So I have to receive all the other n chunks in order to recover any lost packet, right? So the playout delay here is n plus 1, which means that in all cases, if there is any packet loss, I have to wait until I receive all of them. Because the only way for me to recover this lost packet is when I receive all the other n chunks, XOR them together, get the lost one. Okay? So the playout delay here is n plus 1. So in terms of overhead, it's 1 over n, which is pretty low. This is good. All I need is just one extra chunk. Okay? In terms of playout delay, it's a little bit high, because I would be happier if I can just recover this packet once it gets lost, just by looking at the one after it. Okay, I don't have to wait until I receive all of them to be able to recover the lost chunk. But unfortunately here, I have to wait until I receive all the other ones in order to get this one. Okay? What kind of errors can I support here? If I have only one chunk lost in n plus 1 chunks received. Okay? If I have 2, I cannot. All right? Which means that if the probability of error is high, you need to reduce n. If the probability is low, so having lost chunk in every like 1,000 or 1 million chunks, so in that case, have, n is very high. You could have n very high, and in that case, the overhead will be very low. So you can adjust this overhead based on the probability of error. Okay, so that's one technique. It's simple in a way, and these are the performance metrics for this technique. Another technique which tries to increase the redundancy using the concept of piggybacking. Piggybacking works as follows. So for chunk number 2, we will have a low resolution for chunk number 1, which means that I will have to encode the audio using 2 encoding at the same time. One, which is the high quality encoding, which for example is PCM, and in that case I can have a data rate of like 64 kilobits per second, as we said before. Okay? And encode it again using an encoder with a lossy encoder. So in that case, I will have a low resolution encoding of, let's say, GSM, and in that case, the bit rate will be like 30 kilobits per second, or 13 kilobits per second, or 10 kilobits per second. So in that case, it's a low resolution audio, and get the chunk for that correspond to 1 and append it, or we call it piggybacking. Piggybacking talks about the fact that when you send an envelope, just take this with you, or just append this with you, okay? So in that case, the type of error that I can recover, I can have multiple errors, but the limitation here is that they cannot be consecutive. Okay? Because if I lost this one and I lost this one, I cannot recover. خلاص. I cannot recover all of them. I can recover 3 from looking at here, right? But I cannot recover 2. خلاص. Anymore, I cannot recover. Okay? So in that case, I can have distributed types of errors, multiple errors. It doesn't have to be only one error every n chunks, right? But the limitation here is that they cannot be consecutive. Okay? So let's see. So in terms of overhead, how can I quantify the overhead? Well, the overhead here is variable. It's definitely maybe slightly more than the first one. The overhead here is the low quality rate divided by the high quality rate. Right? So so for each high quality rate, I need to add an overhead based on the low quality rate. So, for example, if I have high quality rate of 64 kilobits per second and low quality rate of 13 kilobits per second, so the overhead here is 13 over 64. So I have to add 13 kilobits per second over the 64. So the overhead here is the low quality rate over the high quality rate. What about the play out delay? 2. Bravo عليك. So if I have any packet loss, all I need to do is just to wait for the time when I receive the packet after it. So I need to wait for the time for this particular packet, and if it's lost, I need to wait for the one after it. And I can recover. I don't have to wait for n plus 1. Right? So here it's only 2. Okay? So the overhead is a little bit higher. Well, it depends طبعا on the n in the previous technique. If n is really high and the probability of error is low, then they could be comparable. Okay? But generally speaking here, the overhead is slightly more. The type of errors that I can recover from here is any non-consecutive error. Any non-consecutive error. Okay? Okay, so what if I want to correct 2 consecutive errors? Is it possible here? Yes, it's possible. But not the exact same way. What we need to do now is that we need to look at the chunk number 3 and put a low resolution of 2 and 1. Which means that for each n chunk, put a low resolution of n minus 1 and n minus 2. So if we do this, we can recover from 2 consecutive chunks only. Or any non-2 consecutive chunks. Okay? So if we have 2, it's fine. If we have 3, but non-consecutive, also fine. Okay? But you cannot recover from a 3 consecutive. That you cannot. In order to recover from 3 consecutive, then you have to append another one. But in that case, you will have to increase the overhead. So the overhead will be 3 multiplied by the low quality data rates. Or 2 or something like this. Okay? واضحة? So that's that technique. So the overhead is slightly higher, and it could be even higher if we want to correct consecutive errors, and it depends if we want to correct 2 consecutive errors or 3 consecutive errors and so on. Okay, any questions? واضح? Yes, right. Yeah, so if one packet is lost, if this one is lost, all I need to do is just to wait until the time that this packet should be received. So I detected that I did not receive it, right? So I have to wait for the time of the packet after it, right? And then this packet or this chunk will give me both. Of course, the one that's lost, I will get the low resolution version of it. I will not get the high quality version, but it's fine. I can live with that. Okay. So I have to wait for 2 chunks time in order to play all of them. The other one, I had to wait for all of them because I need all of them to get the lost one, right? I need to XOR all the other n chunks. So I have to wait for n plus 1 anyway.
So if we increase the address of the packet, we have to increase the layout, right?
If we have 2 extra packets, you mean? 2 extra packets, but you need one which is XORed between all the n chunks. What about the other one? The other one, you need a certain function, and you need to make sure that this extra one will give you different information, which is not part of the technique. So what you can make this technique adaptive by changing the value of n, depending on the probability of error. So depending on the probability of error, you can increase or decrease n. You can do that. So that you could do. And to say that I will add another n plus 2, of n plus 2, how can you design n plus 2 in such a way that will give you extra information? So you need to have another function other than XOR, okay? And you need to make sure that this function will give you extra piece of information. So it's not that straightforward. So usually for that technique, they use only one extra chunk, and they change the value of n depending on the probability of error. So all these techniques might be adaptive in the sense that you can change it. Like for this one, I can change whether I append piggybacking for 1 low resolution or 2, depending on the probability of error. If the probability of error is very high, this means that the probability of 2 consecutive errors is very high. Then I can append 2 low resolution chunks.
In case append 2 packets,
Mm-hmm.
2 chunks, lower resolution, the layout will increase also.
3.
Yeah.
It become 3 top. That's if you have 2 consecutive errors. If you have 2 consecutive errors, then it's 3. So it's always 1 plus the number of errors that you get. Yani if you have 2 appended packets, but you get 1 lost. So in that case, by waiting for 2, you can recover, right? But only the worst case is that you can wait for 3 if you have 2 consecutive lost packets.
But why they have to wait? Like they are abandoned together, right?
Right.
So why they have to wait?
ما هو you have to wait until you discover that there is 1 chunk lost, right? And then in order to play out this one and the next one, you have to wait until you receive the next one. Get the next one divided into 2 and play both, right? So you need to wait for 2 packets. In the previous one, all the chunks after the error cannot be played without this one, without the last one. So you have to wait until you receive all of them. Worst case is that you lose the first one. So you have to wait until you receive all the other n chunks, recover the first one from all of them. So the worst case. So here we're talking about the worst case. Any questions? So this technique tries to eliminate the overhead altogether. This technique is good when you have consecutive errors, particularly consecutive error, which is one of the limitations of the previous technique. So on one hand, it tries to recover from consecutive errors without having an overhead. Okay? But of course, this will come with a cost. So this concept is called, or this technique is called interleaving. So we get the chunks, the big chunks, and then we divide them logically into smaller chunks. So one chunk will be divided into 4. Okay? So each chunk will be divided into 4. They are played out in that sequence. So they are played out in that sequence. Okay? What I will do, I will break them into chunks, and then I will interleave them. I will take 1, and then 5, and then 9, and then 13, and so on. Okay? So I did not add any overhead. Okay? Well, except the time required to interleave the chunks. But I did not add anything in terms of chunk size. I did not add any overhead in that case. So in that case, if I have any error, whether it's for 1 or 2 even, it doesn't actually matter so much. What I will do is that I will interleave them back. And then I will have only small chunks in each big chunk that's lost. So in that case, the player at the receiver side might be able to recover from these small errors because the whole chunk is not lost. What's lost is only part of it. Okay? So in that case, they use some techniques at the play out, at the receiver. Some techniques they use like interpolation or something like this. They use like interpolation techniques to try to kind of estimate this from the 3 around it or something like this. Average it out or something like this. In order to play out each of these chunks. Okay? So as we can notice here, although the error is consecutive, but using the interleaving, I was able to distribute the error amongst all the chunks. Yani divide and conquer. It's like divide and conquer. So I have divided the impact of this lost chunk over many, many, many chunks. So the impact on each chunk will be minute, will be very, very small. So the player can recover easily from that using interpolation techniques and things like that. So the good thing about this is that I did not add any overhead, right? So the overhead here, is technically 0, although طبعا interleaving takes a little bit of time, right? What is the play out time here? Play out delay, sorry.
It's the number of the chunks minus 1. Number of all chunks minus 1.
Number of all bits within the same chunk. In this case, because
the play out delay, yes, the play out delay is the number of divisions. It's the number of divisions, but it's multiplied by the play out delay of the chunk itself, not the division. Yani here I divided one chunk into 4, so the play out delay will be 4. But مش 4 times the time of playing the small one. 4 times the play out delay for one full chunk. Why? Because here I will not be able to play all these interleaved chunks until I have to reverse the operation of interleaving. Right? So all these 4 interleaved chunks will have to be played together. I cannot play one before the other, right? Because I have to reconstruct this one in order to play it, right? But this one is dependent on this chunk and this chunk and this chunk and this chunk, right? So in other words, I have to wait for the time required to receive all the 4 chunks. And if I divided these initially into 5, then I have to wait for 5 delays of all the chunks, all the 5 chunks, right? Because the interleaving here will be interleaving between 5 big chunks, right? So I have to wait for 5 complete time to receive 1 chunk. ماشي؟
You said you will not play the chunk and play all its packets are the same.
Of course, of course.
We still have, for
And
example, in the case of packet loss, how the playout will be in case of the packet loss.
In case of packet loss, the packet loss happened here, right? Before I play it out, I will have to do the reverse operation of interleaving, right? So I have to recover all these chunks. And this chunk, in order to recover it, I have to wait for this one, and this one, and this one, and this one. Then, if this one is lost, that's fine. Here, the player at the receiver side will have to deal with this small chunk loss. So they use some techniques to recover from these small errors. Okay? The problem is that one packet can have a significant clip of audio. So if the duration of the audio is a little bit significant, it affects the quality. But if it's small, it does not. So the more number of divisions you have, the better. Okay? So if I increase the number of divisions here, this will allow me to recover from the error in a more efficient way. However, this will affect the play-out delay, because the play-out delay in that case is the number of division multiplied by the play-out delay for one full chunk.
But the technique does not, it helps in recovering the packet loss, or it helps reducing the packet loss from the beginning, right?
It does not. No, it does not. It does not do anything to reduce the error. It recovers from error. It tries to recover from the error. Okay? So either it tries to recover completely from a certain type of error, like the first technique. So in the first technique, I will be able to recover completely, 100%. Given that I have one chunk lost every n plus 1 chunks. Okay, so that's the limitation. And the second one, I can recover from more types of errors, but even the recovery is not 100%, right? Because the recovery is based on the fact that I will have to use low data rate chunks, right? So the recovery here is not 100%, but it's still good. Here, the recovery also is not 100%, right? The type of errors that I can support here is different types of errors, similar to the previous one. And the good thing here is that no overhead. The overhead is 0. Right? So here the play-out delay is the number of chunks. Okay? Of course, multiplied by the play-out delay of one full chunk. Okay? Is the number of division, is the number of division per chunk. The number of divisions per chunk, okay? Which is in that case, it's 4. Okay? Any questions? So these are 3 different techniques. They are very simple. Their idea is very simple, and it's based on the fact that, again, we try to be proactive. In order to be proactive, this concept is used a lot. In order to be proactive, you have to pay an extra cost. And here the extra cost is you have to introduce redundancy. Okay? So here, I don't have to wait for retransmission. I don't have to wait for packets going back and forth. which is what TCP would do. Here I don't have to do that, right? But the cost is the overhead. Of course, this overhead is reflected on the bandwidth, right? So the bandwidth needed for these techniques is a function of the overhead. So for example, for the first technique, the bandwidth has to be increased by 1 over n, right? So instead of sending n chunks with a specific data rate, now I need to send 1 extra chunk for each n chunks, right? So the bandwidth will be increased proportional to 1 over n, right? So if I increase n, assuming that the probability of error is low, this means that the amount of bandwidth I need, the amount of extra bandwidth I need is low, right? If n is small, then the amount of bandwidth I need will become more, which reflects on the fact that the probability of error is high. So you need to reduce n in order to account for this high probability of error, and in that case, you will have to increase the bandwidth requirements. Okay. Any questions? Okay. Let's see. So we'll stop here, inshallah. We don't want to start the new chapter this time. We'll start, inshallah, after the vacation.